on the topic of parametric equations. First of all, parametric equations are very important, not just in elementary calculus, in multivariable calculus, in engineering, in physics, in differential equations, you name it. They give us flexibility. Parametric equations provide a flexible way to represent shapes that cannot be described easily with a single equation. So if you have equation like y equals to f of x, and you have a new parameter or new variable like time or t or heat or anything else that x and y depends on that parameter, you're interested in using parametric equations. This is one of the famous parametric equations that help you to change the format of fonts. Sometimes we use parametric equations because it's much more easier to take the derivative, find the rate of change, or basically calculating the integrals for curves and surfaces. It also provides clarity for us. They provide a clear way to describe motion and paths, which is particularly useful in physics and engineering. Parametric equations have the form x is a function of parameter t, y is a function of parameter t. So in order to avoid any confusion, we're using two function notation f and g. So y depends on t and x also depends on t. F and g are given functions, and the parameter t typically changes over a specific interval, like closed interval a to b. So for example, if you think about time, you might be starting from the first second to the third second, or at the beginning, 0th second to the 10th second, and so on. T might be representing the angle. So for those of you who took trigonometry, you know that you're introducing a new parameter or a new variable like theta. That theta is a parameter, a new variable. The parametric curve described by these equations consists of the points in the plane x and y now can be represented by f of t and g of t. And now we say that, hey, t bounded between a and b inclusive, or you have a closed interval. You can write t belongs to the closed interval a to b. So again, x is f of t and y is g of t. Standard two-variable description is, well, x is connected to y using function f, but now that we are introducing a parameter, t is connected to, or you can say that x is connected to t, or basically you're introducing a new free variable. So here in the standard two variable, the free variable is x, but here when you're introducing t, t is free variable. T is independent from x and y both depends on t using these two functions, f and g. Can always go back and forth between two variable description to parametric description and parametric description to two variable description. Sometimes it is complicated, so don't expect this to be always easy. Consider a parametric parabola. Question says graph and analyze the parametric equation given by x is f of t x is equal to 2 times t, and y is equal to g of t, which is a half t squared minus 4. Okay, what does this guy represent? How do you visualize this? We're going back to algebra. We're going to use the method of point plotting to visualize the path or the curve representing this parametric equation. It says, hey, t is bounded between 0 and 8. So it doesn't want us to just go further to larger t values. Okay, which is a good thing. We have some limitations. So let us construct our table. We're going to start by writing t, which is equal to 0. As you can see, the starting point is 0. And x, which is equal to 2 times t, becomes 0 as well. 2 times 0 is 0. What about your y? Very well. So y, which is defined as a half t squared minus 4, becomes negative 4. Because a half t squared is just 0. 0 minus 4 is negative 4. So x and y can be written as 0 and negative 4. This is going to be our very first point on the graph. When t is equal to 0, your first point is 0 and negative 4, which is located on your graph down here. Let's plug in another t value. Suppose t is equal to 1. Is t in the range? Of course it is. What is your x value? 2 times 1 is 2. What about y value? Y is a half times 1 minus 4, which is negative 7 divided by 2. So x and y in xy plane is going to be the point 2 and negative 7 divided by 2. We can identify this point, which is just right down here. What if t is equal to 2? If t is equal to 2, your x is 2 times 2, which is 4, and the y value is equal to negative 2. If you plug in 2 into g of t, you get a half times 4 minus 4, which is 2 minus 4 or negative 2. So your third point on the graph is 4 and negative 2. Well, you can plug in more values like 3, x becomes 6, y becomes a half, and you get the next point, which is 6 and a half. So as you can see, we're just plotting these points and then connecting them together. And this is the behavior of the curve that you see. If t is equal to 4, x becomes 8, y becomes 4, and the point in xy plane is 8 and 4. Finally, let's plug in 5. You get 10. Your y is 17 divided by 2. So you get 10 and 17 over 2. If t is equal to 6, you have 12, 14, and 12 and 14, which is a point in xy plane. Let us plug in 7. You have a 14, 41 divided by 2, 14 and 41 divided by 2, and finally 8, which is the terminal value for t, gives you 16 for x, 28 for y, and the point is 16 and 28. So what do we see? What's the behavior? We see an increasing curve from left to right. That's why you see these these blue arrows, and this is the curve that you see here. Perfect. So from parametric equations to visualizing what does this guy represent. So if x is equal to 2t and y is equal to a half t squared minus 4, is there any way that we can get rid of t and write this equation in terms of just x and y? From the first equation, x is 2t. So t can be written as a half times x. Well, I have the second equation, which is y in terms of t. Let us do a simple substitution. Wherever you see t, you're going to write down a half x. So your y becomes a half times a half x to the second minus 4. And this guy in turns is y equals to a half times a fourth, which is 1 over 8, x squared minus 4. What does this guy represent? This is basically a quadratic equation. And as you can see, since you have 1 over 8, it is positive, the leading coefficient. So we expect the graph to open up. So from the parametric representation to x and y. So my question for you is, how many parametric representation are available for this function? So if y is equal to 1 over 8 x squared minus 4, how many parametric representation you can create? Well, that's absolutely up to you, right? When you're talking about parametric representation, someone might say, hey, I want to take x to be t, so my y becomes 1 over 8 t squared minus 4. This is your first option, the simplest option possible. Someone else might say, hey, I want to take x to be 2t. So in that case, your y becomes 4 divided by 8, which is a half. You get a half t squared minus 4. Someone else might say, hey, I want to use x to be, for example, 4t. Why not? So your y becomes 16t squared divided by 8, or t squared minus 4. You can continue this process. No one's stopping you. As long as you have a correct algebra behind it, you can have unlimited parametric representation for a function or a curve. Depends on the question. As you remember, we said, hey, this guy has applications in engineering, in physics. So it depends on the context of the question. You might be interested in using different types of parametrization. You might say, hey, can I use sine and cosine? Of course, why not? Anything, any parameter can work here. So you can write down x to be, for example, sine t, then your y becomes 1 over 8 sine squared t minus 4. So you're using a function of t, and then you get rid of that value. This is the basic of parametrization. Sometimes students think that, hey, there is a unique way to represent a function. There is no unique way. You have unlimited format for representation, or you can use different variables like s, theta, anything.